I know. All right, we're going to get started here with the afternoon session. This talk is going to be garbling 3 input AND gates. So please go ahead.
Hi everyone. Am I audible?
Yes, you're good. We can hear you.
Hi everyone. This is Rahul. Today I'm going to talk about our attempts to garble pre-input AND gates directly and how our attempts fail. This is joint work with Omer Shur and my advisor Carmi Sise. The talk will be divided into 3 parts. We first introduce garbling as a concept. The second part would be a detailed intuition to existing schemes that we would need to explain the failure. That's the third part of the talk. So let's start. We're defining a logic gate G as an object having 2 input wires, A, B, and an output wire C. The gate takes in as input x, y, and outputs g of x, y, where g is a Boolean function on the 2 variables x and y. So what do we mean by garbling a gate? Loosely speaking, a garbled gate G hat is an object that lets us evaluate a Boolean function on a secret input in such a way that only the function output is revealed. As discussed previously, on evaluating a gate G on inputs I, j, one needs to obtain G of I, j. Now to garble this gate G, for every wire, we first pick 2 labels of the size security parameter, each representing the wire taking the value 0 or value 1 respectively. For example, if we look at the wire A, we choose, say, A0, A1. In this case, the garble gate has input labels AI and BJ corresponding to the inputs I and J. Now, one evaluates the garbled gate with suitable labels, they need to be able to retrieve the output label corresponding to the output of that gate. Once a gate is garbled, one can apply this technique sequentially to a circuit having some topological order to garble the circuit entirely. We now present a formal definition of garbling schemes as defined by Bellary et al. Without going into further details of what each algorithm means in this particular slide, we note that we are particularly interested in the size of the garbled circuit F. This is a special representation that may optionally have some function hiding properties. Its purpose is to encode the function small f in such a way that depending on the input, this can be evaluated to the function output in some sense. But why do we care about garbling schemes in the first case? Garbling schemes have shown to have a lot of applications to fields like MPC, SFE, zero knowledge proof, outsourced computation, and many more. There have been a long line of work on garbling circuits comprising of 2 input gates, primarily XOR gates and AND gates. Most of them focus on reducing the size of the garbled gate as it increases linearly in the size of the circuit in the gate-by-gate paradigm and proves to be a bottleneck for practical application. Our attempt was to extend such techniques directly to garble 3 input AND gates. In this talk, we will in detail discuss some previous work that directly influences our attempt in garbling 3 input gates. Let's start with Yao's garbling. So garbling as a concept was introduced by Yao in the 80s. For a 2 input gate, one could think of garbling as a set of 4 locks and associated with them a set of 2 keys corresponding to each input. Only these keys could let you open the corresponding lock. If the evaluator is given access to only these 2 keys, then the security of the scheme ensures that it gets access to only one of the 4 locks. To implement what we just saw, we replace the lock and key model in the previous slide with an encryption scheme that encrypts the output labels to be obtained with the input labels corresponding to them as the keys for the encryption scheme. So the garble gate is now represented as a table of the following 4 ciphertexts. When we have the following garble gate, noticed that we could just use a hash function h, given that it is satisfying some properties, to instantiate the encryption scheme in the following way. The problem, however, with sending such a garbled gate is that the order of this table reveals the inputs and the output. There are several ways to solve this issue, but one such technique which is primarily used is the point and permute technique. It was introduced by Beaver et al. It proceeds as follows. We first assign two colors to the labels, say yellow and cyan. We then map these colors to the values 0, 1 randomly for every y. We include the color of the label inside the label itself, for example, as its LSB. We then order the ciphertexts by the color of the label, for example, as shown here. Notice that this order is predetermined and known to both the garbler and the evaluator. The evaluator then decrypts the row corresponding to the color it sees in the labels it has. As the mapping of the color to the value is hidden from the evaluator, the order of values is still hidden with respect to the actual inputs. The first attempt to reduce the ciphertext size was made by Nauer et al., where they showed how to reduce the size of each garbled gate from 4 ciphertexts to 3 ciphertexts. The idea was to set the first ciphertext to 0. In terms of what we see here, this is equivalent to setting the C0 label as h of A0, B1. Notice that this is okay as long as the output of h is random. So now we have three ciphertext garbled gate for any gate G. As said earlier, we focus on circuits comprising of AND and XOR gates. Kolesnikov and Schneider introduced the free XOR technique that reduced the size of the garbled gate for an XOR gate to 0. They did so by introducing a global secret offset delta, such that for every wire in the circuit, the labels are separated by this value. One can then set the output label corresponding to any XOR gate as the XOR of the two corresponding input labels. It's important to stress here that delta is a secret known only to the garbler. Notice that in this case, C0 is to be obtained when the inputs are 0, 0, or 1, 1, or C1 otherwise. It is easy to see that this technique does indeed give the desired output label, as the delta cancels out whenever needed. To summarize so far, we have seen that XOR gates can be garbled for free, and AND gates with 3 ciphertexts. That is, from row reduction, we have that C0 is equal to h of A0, B1. From free XOR, we have that C1 is C0 XOR delta. So the garbled gate for an AND gate now looks as follows. This garbled gate can also be seen as a set of linear equations. The row reduction technique introduces the equation that C0 is equal to h of A0, B1. The rest of the rows of the garbled gate can be seen as ciphertext G1, G2, and G3 that needs to be communicated to the evaluator. Zahur et al. Introduced the half-gates garbling scheme, which showed how to garble an AND gate with 2 ciphertexts. The primary idea of the work in this case was to replace the hash h of A, B with the XOR of the individual hashes of A and B. When we do so, we notice that a lot of these values actually cancel out, and then we get the following garbled gate. In this case, it's also interesting to see that now the third ciphertext G3 is somehow dependent on the first 2, but it also includes delta. In case the evaluator knows delta, then there is no need to send G3, as G3 is just G1 XOR G2 XOR delta. But there is a problem here. As we stressed before, the delta cannot be revealed. It violates the security of the scheme. Zahur et al. Solved this by changing these set of equations cleverly. They add the input label A0 and A1 in appropriate places to ensure that delta is not revealed. and still maintaining that G3 need not be sent. Let us now observe what actually happens when we make this change. We have the following garbled equations. For the first row, the active labels were A0 and B1, and the output label that had to be obtained was C0. The evaluator can now do this in the following way. It can just compute C0 as h of A0 XOR h of B1 as it has access to A0 and B1. Similarly, for the second row, where the active labels were A0 and B0, and the output label still that has to be obtained was C0, the evaluator can compute G1 XOR with A0, XOR with the respective hashes, which will again give us back C0. Notice that in this row, A0 is the active label, and that the evaluator does have access to it and can use it for computing the output label. Similarly, one could work it out for the third and fourth rows, and we see that using G1, G2, and G3, the evaluator can compute what it needs based on the active labels it has. And even better, we need not send G3 at all. G3 is already computable as G1 XOR G2 XOR A0. So AND gates can now be garbled in two ciphertexts, G1, G2, each of size kappa bits. Notice that this actually works even if you change the point and permute bits, in a sense that even if you had permuted the ciphertext otherwise, or the truth table otherwise, this addition of A0 and A1 to those particular places would have worked. Roselek and Roy then showed how to garble an AND gate with 3 kappa by 2 ciphertext in their 3 halves garbling scheme. We now provide an intuition to their scheme. Before we discuss the 3 halves garbling scheme, let's just summarize the half gates garbling scheme once again. In this, Zahar et al. Showed how to garble a gate having kappa bit labels to get a 2 kappa bit sized garbled gate. We also noticed that the ciphertexts in this case have an inherent structure. They happen to be the XOR of the hash of the active label and the inactive label, leaving apart some more labels or deltas included in the ciphertext. Keeping that in mind, we now try to provide an intuition for the 3 halves garbling scheme. To start with, one could slice every label into 2 halves to obtain a left and a right slice, as shown here. Observe that each slice now adheres to the free XOR condition with 2 offsets, a left offset and a right offset, delta L and delta R. So what we have is we have sliced kappa bit labels into kappa by 2 bit slices. What if we garbled each of these slices separately? Remember that for kappa bit labels, we had 2 kappa bit size garbled gate. Now, when we individually garble each slice, say with some half gate like scheme, then we will have a kappa bits garbled gate for each slice. This is still 2 kappa bits, and we did not achieve any improvement so far. However, if we manage to garble in a way where we enforce that both these garbled gates share a ciphertext, then we will have a 3 kappa by 2 bits garbled gate. And this is what the 3 halves garbling scheme does. Before we get into how to garble in such a way, let us see what we need to garble again based on the truth table. For the sake of simplicity, let us now assume that there is no permutation of the truth table. That is, the first 3 rows map to output 0, and the last row maps to output 1. Hence, we need to garble the slices accordingly. So how do we garble each slice? As you remember, we used h of A and h of B to garble the labels in half gates. Here, we will also use h of A XOR B, something which is also computable by the evaluator for the active labels. Notice that due to free XOR, there are only 2 possibilities for the value A XOR B. So as we said in half gates, we used the hashes h of A, h of B in the following way. We computed h of A XOR h of B for each row and used that to encrypt the label corresponding to that particular row in the truth table. Similarly, for 3 halves, Rosalick and Roy suggested that we use the following combination for each row for the left and the right slices so that one could garble each slice separately. Now you can already see that there's a hash of A XOR B that both these slices seem to share in their garbling. And you will later see that this will become the source of the shared ciphertext. Just to repeat, we had the following hashes and the ciphertext in the half-gate scheme. Now, just by looking into this structure, one could guess what the ciphertext for the left and right slices of 3 halves would be based on the kind of hash you use to encrypt the slice. You already notice that the second ciphertext for the left and the right slice seem to be of similar form, except for what is to be added other than the hashes themselves. For half-gates, we already know that this was delta and A0, like we saw it before. Now let us take a closer look at what happens when we garble each slice. For the left slice, we use using the hash combination we mentioned, we have the following garble table. Now this will transform to the following 4 equations. From row reduction, we have that the C0L is the following value. Similarly, one could work this out and see that you have G1L, G2L, and G3L as follows. Notice that G3 is now again G1 XOR G2 XOR delta on the left slice. Similarly, the right slice equations are as follows, and you will again see a similar structure. Listing both these together, we see that these two indeed share a ciphertext. However, the same problem as in half-gates presents itself again. Delta cannot be revealed. First attempt would be to solve it like we did in half-gates. So, does this work? It does, but not completely. What happens is that what we add now becomes dependent on the permutation of the truth table. So based on the permutation, we will have to add different things. And revealing what we are adding to the evaluator leaks the permutation, which is not desired. So what do? We actually first fix the permutation, then add some labels to each equation such that the problem is solved, and then encrypt the combination of slices that we have actually used and send it to the evaluator. That way, the evaluator gets to see only what it needs to use for decryption and nothing else. However, we will not discuss how to encrypt the combination used as it is out of the scope of this talk. We now present our attempt at garbling 3-input AND gates. Traditionally, a 3-input AND gate is garbled by representing it as a sequence of 2 2-input AND gates as shown here. Hence, to garble the 3-input AND gate, one will need 2 times the size of the garbled gate for a 2-input AND. Even if you use 3 halves, this would be a 3 copper bit size garbled gate. Our question is if we can do better by directly garbling a 3-input AND. A 3-input AND gate, which is garbled, will have input labels AI, BJ, and CK. And one needs to retrieve an output label D based on the values I, J, and K. We stress at this point that techniques like pre-XOR and point and permute extend to higher input settings unconditionally, and we don't discuss it here and assume it. Again, assuming no permutation to the truth table, garbling a 3-input AND gate means to encrypt D0 for the first 7 rows and D1 for the last row. We observe that in this case, which is the 3-input case, we have more number of hashes that are available, and maybe we can use these and slice more. We have, apart from H of A, H of B, and H of C, we have H of A XOR B, B XOR C, A XOR C, and A XOR B XOR C. So the slicing mode actually helps. We now show by assuming 3 slices. Let's slice each label into 3 parts. So we have the following structure with 3 different 3 XOR offsets, say delta 1, delta 2, and delta 2. This will correspond to garbling 3 slice truth tables, just like we did for the 2 slice truth tables in the 3 halves case. Again, for the sake of simplicity, let us assume that there is no permutation of the truth table. That is, now the first 7 rows map to output 0, and the last row maps to output 1. So, how do we garble each slice in this case? Just like we saw in half gates, we will come up with hash combinations to use for each. For the first slice, we use h of a XOR b XOR h of a XOR c, h of a XOR b XOR c. Similarly, for the second slice and third slice, use the following hash combination. It is interesting to see that these slices actually do share hashes between them, and that might be a source of reducing the size of the garbled gate itself. And this was our intuition. We just now concentrate on the first slice. As stated, we use the hashes a XOR b, a XOR c, and a XOR b XOR c for the first slice. That translates to the following ciphertext for each row. Notice that the 0 label is included in all 8 rows and delta in 1 row based on the truth table. We split them up now for ease of representation. Furthermore, the part corresponding to the hashes are made of just 6 hashes, as you can see in the slide, which is used in a particular way. This can also be represented as a matrix vector multiplication. This was already done for 2 input gates by Rozulik and Roy in the 3 half garbling scheme. Finally, we introduce appropriate vectors to ensure that the entire right-hand side is represented as a linear equation. The equation on the right now represents the final garbling equation for the first slide. We repeat the process as we did in half gate, determine how many ciphertexts are needed to be sent to the evaluator for it to be able to compute the first slice here. Extending the approach in 3 halves, based on solving linear equations, we were able to determine that one would have to send to the evaluator these following 3 ciphertexts so that it can derive the output side. Just like in half gates, it turns out that they are the XOR of the hash of the active and inactive labels. Again, apart from some labels or deltas included in the ciphertext. All the other rows can be derived using these 3 ciphertexts for the first slice. As usual, the first row is the 0 ciphertext based on row reduction, which gives the following value for D01 and sets the ciphertext to be 0. Though it might not be completely clear from these slides, one can work out that the following are the combinations of G1, G2, and G3 that one could use to derive all the ciphertexts in this table. Let's rewrite this like the table we know for the 2 input case. This looks very similar to what was done in half gates and 3 halves and looks really optimistic at this point. But what goes wrong? Notice that the delta problem has yet again resurfaced. However, there's a catch this. One cannot find any linear combination of input labels that solves this issue for the 3 input case, even for one slice, let alone think of all slices together. It is disappointing, as if this was possible, one could just extend this to get a 4 kappa by 3 bit sized garbled gate for the 3 input case, which obviously was extremely optimistic in the first place. To conclude, I would like to highlight that we only saw one possible extension in this presentation and illustrated as to why that extension doesn't work. And this in itself doesn't even cover a part of what's actually not possible. We have tried multiple other extensions that look very similar to this, using other hash combinations, more slicing, etc., and were unable to achieve a garbling scheme of size less than or equal to 3 kappa bits, which is what 3 halves would give. The extended abstract provides more detailed algebraic overview if you're interested. Last but not the least, I would like to end the talk with some questions to ponder about. Is nonlinearity good or bad for garbling schemes in general? Can we introduce any nonlinearity to achieve a better scheme for higher fan-in gates? So by nonlinearity, I mean that the inability to express these garbling schemes as a set system of linear equations. It's not exactly clear at this point if nonlinearity is good or bad. We have seen that linearity is good for like XOR gates, and it also actually is a necessary thing to be able to garble using 3/2 or using half gates. So this is one question to think about. Also, understanding the sliced garbling setting in general remains a quite widely open problem. With this, I would like to end my talk and open up if there is any question. Thank you.
All right, let's thank our speaker. We do have time for questions, so if anyone in the audience would like to come up to the mic. In the meantime, I do have one question, and beautiful slides, by the way. These are these are really nicely done.
Thank you.
I was thinking throughout as you were sort of putting all these equations on there, that this is a very kind of algebraic centric viewpoint of how to look at this. Have you thought about, are there other frameworks for playing around with these kind of things, like maybe a more geometric sort of framework, or even when you're talking about nonlinearity, are you still imagining kind of analyzing this in an algebraic way, or are there other sort of ways of thinking about it that you guys tried?
So there are like multiple ways to think about nonlinearity here. In some definition, you can actually view the 3/2 scheme itself as a nonlinear scheme. But it's actually a good question and something which I don't think is explored well in the garbling setting, at least for like efficient garbling. But actually just say that I am at this point not sure, and that would be something to really think about. But I'm not sure if there are geometric constructions. It's at least as far as I know, I haven't seen any.
All right, thanks. And one other question is just, at this point, if you had to make a bet, do you think that bound of the 3K is going to hold up, or do you think there is some way to beat it?
If you just have like direct extensions like the kind I showed here, then probably not, but maybe with some variations in it, and that would basically maybe what would be non-linear about it.
That's a pretty diplomatic bet. But let's thank our speaker again. Thank you very much.
Thank you.
Okay, I will note this is the end of our virtual program for CFAIL, but we will be back in person after the coffee break here. We'll be back at 3:55 for an open problem session. So bring your favorite open problems. We're going to discuss them in groups, and then we're going to get up and present the open problems and give out some t-shirt prizes. So please come back after the coffee break. Thank you.